So today we're looking at question 3 from the 2018 MAT paper. This is one of the long questions, so there's quite a few parts here. Let's start off with the first part. So it's telling us we have this function g, which is defined in two different cases, for x non-negative and for x non-positive. And it's also telling us m of x is the gradient of the chord between the coordinates 0, g of 0, and x, g of x. So we'll get to that later on. But for the first part, we are asked to sketch the function g of x just on the interval x between -3 and 3. So we'll do that first. Okay, so we've got a function g up here, and this is composed of two quadratic functions in two different cases. So we just need to consider each case separately to plot this function. So I'll draw the axes here, the xy plane, and first off, let's look at where the y-intercept is. So funnily, it's kind of defined, the point x equals 0 is defined for both cases. So we'd expect that they would agree in both cases. So if we put x equals 0, we get -1 squared plus 1, which is 2. And in the second case, we get 3 minus 1 squared, which is also 2. So that's good, which means when x equals 0, it's going to equal 2. So that's the y-intercept. And now let's consider the case when x is non-negative. So this is a quadratic function. It's going to tend upwards and it's going to have a minimum. And because this is already in the completed the square form, the minimum is just going to be at the point where this bracket is 0, so where x equals 1. So if we write this as point x equals 1, this is going to be the minimum of this quadratic on the right hand side. And this takes value 1. So if we look at some other points 2 and 3, we can quickly plot that when we put x equals 2 in here, we have 2 again, and then 3, we have 2 squared, which is 4 plus 1, so 5, so it's going to be a bit higher. So on the right hand side, it's just going to look like a part of a quadratic function that looks like this. And then when x is non-positive, it's going to be a similar story. We now have again a quadratic function, but we have a minus x squared term, so it's going to tend downwards. And here the maximum is going to be at x equals -1 when this bracket is equal to 0. So if I draw this as -1, the highest point is going to be when x equals -1. And that's going to be when this bracket is equal to 0, which is when y equals 3. So that's 3, this is 1. And then let's also test the values for -2 and -3. If we put -2 in here, we have 3 minus 1 squared, which is just 2 again. So it kind of dips back up, back under to the value of 2. And then for -3, we have 3 minus 2 squared, so we're going to have -1. So this is going to be quite a rough sketch, but if this is -1. So then our graph is going to look like this. Very rough sketch, but you get the general shape. We have two turning points at x equals 1 and x equals -1. So that's how to plot this function. So going back to the question, we are now looking at part 2. And it's asking us to write expressions for the function m of x in the two different cases when x is positive and when x is negative. And remember that m of x was defined as the gradient between the chord that goes through the points 0, g of 0 and x, g of x. Okay, so for part 2, we need to define this function m of x, which is the gradient between the points 0, g of 0, so the y-intercept, where g goes through the y-axis, and just an arbitrary point on this curve, so x, g of x. So the gradient, if this is the chord, we need to find the gradient of the slope. And to do that, it's just a very general formula. I'll write m for the gradient. This is going to be the difference of the y components, so I'll write y2 minus y1, divided by the difference of the x components. So this is going to be our formula for the gradient, and this is what we're going to use to define m of x. So let's consider when when x is positive first. Then m of x is going to be just g of x, which is this point here, g of x minus g of 0. And we know that g of 0 is just 2. So it's going to be just a top case, so we have x minus 1 squared plus 1 minus 2. So this is our first point, that's our second point. And then we need to divide by the difference of the x coordinates. And this is just x and 0. So on the bottom we just get x. And this is for the case when x is strictly positive. So we can actually do some simplifying here. If we expand out these brackets, we get x squared minus 2x. Then we'll have plus 1 plus 1 minus 2, and you're going to see the constants are going to cancel out. And then we still have the x on the bottom. So if we don't have any constants, then we can cancel out the x's, which means we're going to get x minus 2. So that is what m of x is when x is positive. We can do a very similar thing when x is negative. We just replace this expression with the one on the bottom. So I'll also write m of x is 3 minus x plus 1 squared minus 2 divided by x. And if you do the algebra, if you simplify everything, we're going to get very similar. We're going to get minus x here, minus 2. So that's what m of x is in the case x is less than 0. So I'll just highlight this. We have x minus 2 and we have minus x minus 2. So that's what m of x is. Okay, so part 3 of the question is asking to show that m of x plus 2 equals x when x is positive, and also to find the value of m of x plus 2 when x is negative. Now I've actually lost the footage for this part of the question, but if you just go back to part 2, then it actually follows immediately, just by adding 2 to both sides, because we found an expression for m of x, so just go back and rearrange that. It should be fairly immediate. So let's look at part 4 then. This is a bit harder. We need to explain why g has derivative minus 2 at 0. Okay, so remember what our function m of x was, and let's just quickly remember what it meant graphically. So if we had a function g which looked something vaguely like this, then m of x was the gradient of this chord. So for any value of x, it gave the slope of this line. So to find the gradient of g of x, we can think in terms of m of x. So if you think about x tending towards the origin, which is the point we need to find the derivative at, then this line is going to get closer and closer to 0, and it's actually going to approximate the tangent at the point 0. For small values of x, it's going to approach the gradient. And that is exactly what the derivative of g is going to be. So the idea here is that as x tends to 0, m of x is going to tend to the derivative of g of x. So let's just write, as x tends to 0, m of x tends to the derivative of g of x, which is what we just said. So it tends to g dashed of 0. Because that's the derivative of g at the point 0. And then we just need to work out what this is. So we can say m of x, this tends to, well, let's just look. The x's are just going to vanish to 0. So in both cases, we're going to have minus 2, which is good because it means the derivatives are agreeing on both directions. So from the right side and from the left side, the gradient's going to be minus 2, which is good. So m of x tends to minus 2. As x goes to 0. And that is how we justify that. So I'll just write, therefore g dashed of 0 is precisely minus 2. And that's quite a short question. You just need to understand that m of x is actually approximating the gradient, the derivative of g at the point 0 for small values of x. So we deduce that g dashed of 0 is minus 2. Okay, so now we're on to part 5 of question 3, and I believe this is the hardest part of the entire question. So let's just read what it says. It says, suppose that p is strictly less than q, and that h of x is a cubic polynomial, and it has a maximum at the point p and a minimum at the point q. Then we need to show that the derivative of h is negative whenever x is in the interval between p and q. So let's have a look at this. So in red, I've just written the information we've been given to us. P is less than q, h is a cubic, and it's got maximum at p and minimum at q. And we need to show that the derivative of h is negative. So let's try and consider what h dash would be. So if we know h is a cubic, then we know that h dashed of x is going to be quadratic. So h dashed of x is a quadratic. That's just from differentiating a cubic. You're just going to reduce the power by 1. So we can just write a general formula for h dashed, and we know that it has a maximum at P and a minimum at Q. So that means it has turning points at P and Q, which also means, just from the definition, it means that h dash of P equals 0 and h dash of Q equals 0. So that tells us that P and Q are roots of this polynomial. So we can write x minus P, bracket the wrong way, x minus P times x minus Q. And we also have some constant, let's call it C. So then this is a quadratic polynomial. It's got highest power 2, and it's also got roots at P and Q. Then we've also have a constant which we don't know yet. We need to find some information about this. But this is how we can express the derivative of h. Okay, so now we've expressed h as h dash as this. It's a quadratic. We can think about its graph. Very generally, it's going to have two roots. We don't know where it's going to lie, but let's just write P here and Q here. We know P is less than Q. And if we can show C as positive, then we know this quadratic is going to be tending upwards. And that means it's going to be negative in the interval between P and Q. So that's exactly our strategy for this question. We're going to try and show that C is non-negative, so that this function has this shape, and that would prove that h dash is negative in this interval. So to do this, we're going to try and find the second derivative of h. And the reason we do this is because we also have some more information that we're given. So if we know that P is a maximum, we know second order information. We know that h double dash of P is going to be less than or equal to 0. And since Q is a minimum, we know that h double dash of Q is going to be greater than or equal to 0. So that's just from definition of maximum and minimum. And so we've got this information, the second order information, and to use this, let's calculate the second order derivative of h. So this is fairly standard. We can use the product rule, we can expand this out however you like, but then it's going to come out as c times 2x minus p minus q. So that's the second order derivative of h. And then to work out the sign of c, we can sub in some values. So let's use this information. We know that h double dashed of p is less than or equal to 0. And this comes out as, we'll have 2p minus p, so we'll have c times p minus q. And from up here, this is less than or equal to 0. But we also know that p is less than q. So this is going to be negative, strictly negative. So to satisfy this inequality, that tells us that this implies that C is strictly, not strictly, it's non-negative. So let me just recap that. So we knew that the second order derivative of h at P is non-positive because P is a maximum. So we input that value into the derivative and we get this formula. And we know that P minus Q is negative because we're told in the question that P is less than Q. That's just rearranging this inequality. And then the only way that this inequality can be true is if C is non-negative. So now that we've shown that, let's just remember what we were saying earlier with this quadratic. This tells us that the first derivative of h is a quadratic with this shape. And then we can see that it's always going to be negative in this region. So to conclude, we just write h dashed of x is negative when x is in between q and p. And that's how we proved it. We just showed that this constant was non-negative. And that's the answer to this question. Okay, so now we're on to part 6. This is a very long question, but we're getting towards the end. So now we need to suppose that we have two real numbers, c and d, and we are given a cubic polynomial, h of x. This is similar to before. Now the maximum is at -1, and the minimum is at 1. And we also have the derivative of h at 0 is equal to -3c, and the y-intercept h of 0 is equal to d. So given this information, we need to show that c is strictly positive, and we also need to find a formula for h of x in terms of c and d. So this is going to be a little tricky, but we can do this given the information we have. Okay, so for this question, we are actually going to adopt a very similar strategy to the previous part. So we actually fall into the previous case. We have a cubic polynomial, we have this extra information, but we have a maximum at -1 and a minimum at 1, and -1 is less than 1. So that tells us from the previous part that h dashed of x is negative for x between 1 and -1. So if we, so this tells us immediately that h dashed of 0, which equals -3c, this is negative, just from the previous part, and that implies that c has got to be positive. So that's the first part of the question. It's fairly straightforward, it just follows from the previous part. Now, to find the formula for h of x, we actually use a very similar strategy to before. So we consider the derivative of h, and we have some information. We know that h has a maximum at -1 and minimum at 1, so h dashed of -1 equals 0 and h dashed of 1 equals 0. So that means we can write h dashed of x as x minus 1 times x plus 1. These are the roots of this polynomial, and we're also going to have a constant. I'll write capital C again. So this is a quadratic, so it satisfies our conditions. It has roots at -1 and +1, and we also have this constant which we don't know yet. And then to find h of x, we can just integrate this once we know what the constant is. Now, to find the constant, it's fairly straightforward actually, because we have this information of what h dashed of 0 is. So if we just input that value, we're going to have h dashed of 0. Just putting x into this formula, we have -1 times +1, so we're going to have minus capital C. And just using the information we've been told, this equals -3 little c. So I hope you can tell the difference between these two. But it tells us that this constant capital C is just equal to, so c equals 3c. So we can write h dashed of x as 3c times, I'll just expand these out to make it a little easier, x squared minus 1. So this is h dashed of x. Now we can integrate this. This is fairly straightforward. Just integrating a polynomial to get h of x. And we're going to have, so the 3, we can, so I'll just write it out. We have c times x cubed. Think of opposite of differentiating this. The 3 is going to vanish. And we're also going to have minus 3cx. And then we also have a constant, another constant from integration. I'll write this as k this time. So the last part of this question is to work out what the constant k is. And then to do this, it's fairly straightforward because we've been given some more information of what the y-intercept of h is. So if you imagine putting x equals 0 into here, all these terms are going to cancel out, that's going to cancel out, that's going to cancel out, and we're just going to be left with k. And we're told that this k actually equals d. So I can rub this out and I can replace it by d. And this is the exact formula for h of x in terms of c and d and x. So we're on to the final part of the question, part 7. And for this, we need to show that there are no values of c and d from the previous part, such that the graphs of g of x and h of x are the same for the interval -3 to 3. So let's just think about this. So intuitively, it kind of makes sense that these can never agree because g is defined in terms of quadratics and h is defined in terms of a cubic. So intuitively, this should make sense. So we shouldn't be able to find constants such these two functions are the same. And we just need to prove that mathematically. So we've got our two functions, g of x and h of x, and we need to show that they're not equal for any constant c and d. So what we're going to try and do is we're going to evaluate these functions at some point to put constraints on these constants to find what they have to be, and then we just deduce that these functions aren't the same. So as a first step, let's work out g of 0, which we know already. This is equal to 2. We saw this earlier, and if these functions are the same, then we would have to have g of 0 equals h of 0. That's just a must. And if you remember from the previous part, or you can just work it out quickly, then h of 0 is equal to d. So this tells us that if these two functions are the same, then we would have to have d is equal to 2. And we can use a similar trick. You could evaluate at different points, like x equals to 1, to work out what c is. What I'm going to do is a little bit quicker. I'm going to evaluate at the derivatives of g and h at the point 0. So if these functions are the same, then we'd have to have that h dashed of 0 equals g dashed of 0. That's a must as well. And if you remember from the last part, we were told that h dashed of 0 equals minus 3c. And also from the previous part, we worked this out using the function m of x. If you remember, we worked out that this g dashed of 0 equals minus 2. And this just immediately tells us that the constant c has to equal 2 over 3. So this is just a little trick to get there quicker using the previous parts, but you could also work out what c is by evaluating a different point. It works as well. Anyway, this tells us that if these functions are the same, then we have to have h of x is now defined as 2 over 3 x cubed minus 3 times 2 over 3, which is minus 2x plus 2. So we've put constraints on these constants, so if these functions are the same, then h of x has to be defined like this. But now they can't be true. We have a cubic and we have two quadratics. To show they're not the same, we can just evaluate at another random point, and it's fairly easy because they're not going to agree on most points. So let's just take a simple point, x is equal to 1, because we know they agree at 0 just by how we constructed it, but they don't have to agree at 1, and we're going to show that. So h of 1, if we put x equals 1 here, we have 2 over 3 minus 2 plus 2, so we have 2 over 3. But if we put g of 1, we would expect this to be the same if they're the same function, but in this case, x is positive, and we have x at 1 minus 1, which is 0, plus 1. So g of 1 is equal to 1, and we immediately see that these are definitely not equal. So if they're not equal at a single point, then they definitely can't be the same function. So we conclude that h does not equal g, ever, for any values of c and d. And that's the end of this question.